In this video, we'll be demonstrating how to analyze data that have come from a randomized complete block design experiment using R. Now I'm going to be using a data set from chapter 4. I think this is from problem 13, where we're sending 3 different types of design materials, advertising materials, and determining the number of responses that we're getting. Now this might look very similar to a different situation that you're dealing with. And in this case, we know that we're sending these response materials and these different designs to people in different regions of the country, and we want to account for this. Now, in the YMCA case, we don't have to worry about accounting for any of this information because we're keeping it nice and simple. But if we were sending it to people in different regions, this could be a blocking factor that we could account for. So first of all, it's so important to note what is missing when we move on to the analysis stage. Remember, so many things have already gone into this. And one of the most important ones from our perspective is the randomization. This does not show the randomization procedures that have happened, but as a statistician, especially if you're using the randomized complete block design, remember that's what separates a block from just another factor. So if we just randomly sent these out into random regions, then we would maybe use region as a second independent variable, but in this case we're randomizing within region. So within the Northeast, we randomly do design 1, design 2, and design 3 to split between those different groups. So remember this randomization procedure that's so important and contributes to our definition in some of the cases that we go through. All right, so first I'm going to go ahead and I'm going to read in my data. Looking at this data, what did I call this data? I called this C4P13, C4P13.csv. And now I'm going to look at the top of my data set to make sure it looks good. What I'm looking for is making sure design, region, number of responses read in. Now I've got this weird X factor. I don't particularly want that, but it's not really hurting anything. You could choose to remove it, and why not demonstrate that? Dat -1, this just takes out the first column. Now be careful here. Note that if I look at the top of my data set, now it's removed, but if I run this line again and then look at the top of my data set, I removed again the first column. So you want to be careful about writing kind of generic code that will always remove the first column. I'll run all of this and just make sure that I don't run this quote unquote remove the first column line one more time. Now the first thing I'm going to do is I'm going to fit my model. So I have the data set in here. Now note how we could use the apply function to get the sums of squares across all of these in the different groups. So we could do those yij's, that y dot dot bar. So if we wanted to do this real quick, let's see, y dot dot. This is going to be the mean across all of our data. So this is the mean of dat number of responses. That's going to be our y dot dot. Our yi dot. Now remember, we want to take each of the designs, so design is going to be our I, and we want the mean within each design across all of the different regions. We demonstrated this using the aggregate function in class before. So we're going to aggregate the number of responses by the design. Oh, and I need to give it my function. So I'm going to take the mean within each of those designs, and that gives me my yi dot. And again, you can do this by hand, and in fact, if you're confused as to what this code is doing, I highly encourage you to go and calculate each of your yi dots by hand and each of your y dot j's by hand so that you can see what's going on in this case. Now here I'm going to do this not just by design, but I'm going to do this by region now. And this gives me my y dot j. And so now I can use my equation. So remember, I guess I should write in I guess I'll use what the textbook uses. It uses A and B. So A is the total number of levels of the factor. So if this is the case, I could just use table dat $design to see how many different levels of the factor there are. If I wanted to do this programmatically, I could do length of that table, but instead I'll just type in 3 here. B, I'll do the same table command to see how many different regions there are. There's going to be 1, 2, 3, 4 regions, each with 3 observations in it, so B is going to be 4. Now remember what my sums of squares for the treatment was. My sums of squares for the treatment was A times the sum of y I dot minus y dot dot quantity squared. The sum of squares for the block was very similar, B times the sum of y, now instead of being I dot, it's dot j minus y dot dot quantity squared. Oops. What did we do wrong? Not meaningful for factors. Nope. Oh, I have an idea of what happened. Looking at this, aha, I see. Instead of just listing my mean responses, which should be the second column, I accidentally assigned it the whole matrix. So I need to tell it to just take the second column from this aggregate matrix. I'm going to use my bracket notation and do comma 2 to indicate the second column. Now I need to double check that, y ID, and make sure, yes, now it's only my second column, that is each of the means within each of the designs. I'm going to have to do this for both cases. And I'm glad R caught me on that. Would have completely forgotten otherwise. So that's my sum of squares for blocks, and I can make sure that this is coming out right. Sum of squares treatment, sum of squares blocks. Okay, that's looking okay by hand, and eventually we'll check this, of course, with software. Now the sum of squares error is going to be a tough one. So remember, we can do what the textbook did and just do the sum of squares for the total. So the sum of squares for the total took every y value and subtracted the grand mean from it, and then squared that and added them all up. So sum of every y value, so all of the y values are all of these responses, and we're going to subtract the grand mean, y dot dot bar, from it, and square this term. So this is the sum of squares total. Now for our calculation for the sum of squares error, remember now that we have all these pieces, sum of squares total minus sum of squares between minus sum of squares treatment, and that gives us a sum of squares error. Now for the final components that we have to add, we just need our degrees of freedom for the treatment, which is a minus 1, degrees of freedom for the blocks, which is b minus 1, the degrees of freedom for the error, which is a minus 1 times b minus 1. And if you're not sure where I'm getting these equations, go and double check your notes to make sure you can follow along with where these came from. And now I can calculate the mean squared treatment, which is the sum of squares treatment divided by the degrees of freedom for the treatment, the mean squares block, which is the sum of squares for the block divided by the degrees of freedom for the block, and then the mean squared error, which is the sum of squares error divided by the degrees of freedom for the error. Now previously we had you put together a manual ANOVA table. We're not going to worry about that here. All we're going to get you to do here is to calculate this F statistic MSTR divided by MSE. Now this is a ratio between the treatment and the error, so we can find our critical value. Remember, to find our critical value, I can never remember personally if it's PF or QF, but you can always look in the documentation, question mark QF. So we give it the probability that we're interested in. So for a 95% confidence interval, 0.95. The degrees of freedom for the numerator, that's the degrees of freedom for the treatment. The degrees of freedom for the denominator, that's the degrees of freedom for the error. And remember that we want this lower tail to be false. We want this to be an upper tail value. Excuse me, P should be 0.05 for the upper tail value. So we want 5% of the data on the upper tail. Now in this case, this means our cutoff is 5.14 and our observed test statistic is 17. So because 17 is greater than 5.14, we would reject the null hypothesis. Remember that the null hypothesis in this case is that all of the means are the same. So we have evidence to believe that not all of the advertising methods are the same after accounting for that blocking factor. That's what we can interpret here. Now it's time to double check. So to double check this, to run our model using the built-in functions in R, we use the AOV command just like before. Now I'm going to get my variable names from DAT so that we can use this. So I'm going to have the number of responses as my outcome. I'm going to have the design. Now this is what we normally did. Design data equals DAT. This is what we had done before. To add in another variable in the formula notation, we actually use the plus sign. So the plus means add a variable. Note that plus, minus, squared, some of these other things don't necessarily mean plus. So we're not taking the column design and adding the column region. In the formula notation, plus means add a new variable to the model. So we're going to add the variable region to the model. Oh, and this is case sensitive. So number of responses. Now the first thing that I would normally do is I would run my assumptions checks, and this is very important, but right now I'm kind of worried about my degrees of freedom, specifically because design, if I look at my data, design's being read in as a number, and I know sometimes R has trouble with that. In fact, I might just go ahead right now and use as.factor for design so that I don't run into issues. If you wanted to, you could just double check your degrees of freedom in your model real quick to make sure R is reading that in appropriately so that you don't have to worry about checking it now. But from here, this is where we go forward and we check our assumptions, checking assumptions. So let's make our residual term. So we can just look at the residuals of the model. And that gives me my error. So I'm going to do first normality. So QQ norm and then QQ line. So looking at the normality plot and the line. This normality plot doesn't look particularly great, honestly. I'm pretty concerned about these couple outliers on the top and bottom. I'm not particularly impressed. What we can do is we can follow up with a Shapiro-Wilk test just to see. Shapiro test of E. This indicates the p-value is greater than 0.05, so this indicates no violation. Honestly, given the test, or given the image, I tend to believe the image, not the test. In this particular case, because there's so few data points, the test isn't particularly reliable. We're going to go on and move forward here, but this is something to be aware of. Hey, in this case, normally I would stop. I would move on to a non-parametric test that doesn't assume normality, just because this normality plot actually looks pretty bad. So even though the Shapiro-Wilks test looks okay, I trust my eyes in this case more than I trust that statistical test, which incidentally is why we tend to not worry about doing the statistical tests, because even if the statistical tests disagree with what our eyes are telling us, I trust my eyes more than the test. All right, so the next thing I'm going to look at is this homogeneity of variance assumption. Now, in the homogeneity of variance assumption, there's a couple of different ways we can do this. We can look at this homogeneity of variance by plotting the predicted versus the residual. So plot, we have on the x-axis these residuals that we were looking at. On the x-axis, we have the predicted. That's the fitted model. And then on the y-axis, we have those residuals that we made. So this is a plot similar to what we saw earlier. Now we've got some variability here, and we've got a few points that are just jumping out. These, for whatever reason, seem to just not fit with the rest of the model. Seems to be a couple of outliers here, and I'm not quite sure why. So that's definitely something to check in. It's definitely what we saw too earlier. We've got 1, 2, 3, 4 points that seem to not really be fitting with the pattern. So something strange seems to be going on. Looking at this, I'm not seeing a pattern of change. I'm not seeing a pattern that I'm noticing. That doesn't mean, well, it does mean that maybe my homogeneity variance assumption isn't super challenged, but looking at these outliers, this means that something strange may be going on with the data set. So actually moving forward here, I'm not as worried about the assumption because, again, for the majority of the data, it seems fine. What I'm more thinking is that maybe something is making these 4 points to be different, both in the residual plot and in the normality plot. So that's what I'm thinking through as I'm reading through this. Again, independence comes from the design. I don't know anything about the design. We could read in the textbook a little bit more. Let's see, reading the textbook problem. Looks like that they have sent this to 500 samples of potential customers in 4 regions. There's 5,000 samples. It looks like there's no reason to believe that in any of these samples, the samples are somehow related in a way that's not included by the model. So I don't have any reason to believe that there's a violation of independence here, though it is something to consider. So now that we've checked through our assumptions, I'm really curious to see the summary of the model. I'm really interested to make sure that my degrees of freedom are right. So the factor degrees of freedom are correct. The region degrees of freedom are correct. You know, another thing that I'm going to do real quick here is I'm going to run a box plot. So I said earlier that I think I was looking at a couple outliers. I want to run a box plot to see where those outliers might be. So number of responses by design, data equals dat. Let's see if they jump out anywhere here. So I don't see any real outliers looking here. Let's try the region though. So instead of just doing this by design, let's also do this by region, and this was demonstrated in our slides. So this is kind of interesting. So looking at the region, I see that all of these tend to be very, very skewed towards the top. Note how close the median is to Q1, and note that there appears to be some big jump going on here. So this is very, very skewed upwards in this data set. Now I'm not sure if this is traditional. It doesn't look like. I didn't notice this pattern of skew. I guess I can check in the previous plot. Yeah, there's no pattern of skew here in the previous plot. These seem pretty symmetric, but there's definitely a pattern of skew here going on in the region plot. So it definitely seems to be something about the blocking factor that's creating these skewed images in terms of our homogeneity of variance and such. Looking at this though, the homogeneity of variance within each of my groups seems to be fine. Normality within each of my groups seems to be fine. So actually I'm more comfortable moving forward with assumptions than I thought. And again, this came from identifying that there's a couple of outliers. I've now identified where the outliers are coming from. They're coming from these regions, not from my variable of interest. So I'm okay because I'm not going to be remember the violation of statistical tests of statistical assumptions affects your interpretation of statistical tests. So if I'm not interpreting statistical tests about region, and I'm not because they're blocking factors, I don't care about the region, then I can go on and move forward with statistical tests regarding my blocking factor that I do care about, which is about the design. So I'm going to clear this out. That definitely sets me at ease looking at those blocking factors and figuring out where this weird stuff is coming from. And I'm going to go ahead and look at the summary of the model. So looking at the summary of the model, I can see here that my design factor, we've got 2 degrees of freedom, we've got some sums of squares and such, and I've got my probability, my p-value being 0.00018. So this is statistically significant, very statistically significant. And I'm going to go on and ignore this second line. So again, as we mentioned in the previous video, sometimes software will give you statistical output for a blocking factor, and you might not particularly care. So when software is giving me the statistical output for a blocking factor, I'm just kind of mentally ignoring this. It's not really going to have much meaning, and again, that's because the randomization within the blocking factor makes interpretation of the statistical test sketchy at best. And again, it depends on who you talk to about if it's even possible to interpret this test. The only reason we would look at this is to determine should we include region in a future test. So if we were doing this experiment again, should we include this blocking factor? Because this factor is statistically significant, we would tend to say yes. If we were doing this, we should include this blocking factor. But for the purposes of our current research, so that would be for future research. For the purposes of our current research, this isn't particularly interesting. What we're focusing on is design. So our big research question was, does design matter? Does design matter? And according to this, it looks like yes, design absolutely matters. The design factor is statistically significant, so different designs are important to take into account. Now, because I've presented 3 designs, if this was random effects, if I were randomly selected the number of designs, usually not going to happen, but maybe. So if this were random effects, I would look at the variability components. Because I believe this is fixed effects, I'm going to look at these specific designs. So I'm going to go back to my box plot for each of the designs, and I'm going to look more in depth at this now that I know that there's a statistically significant difference. So looking at the number of responses, I see that the number of responses in design 1 and the number of responses in design 3 are definitely seeming to be lower than the number of responses in design 2, way lower. In fact, the minimum of responses in design 2 seems to be higher than the top peak number of responses in design 1 and 3. So this definitely seems to be clear evidence that design 2 is kind of an outstanding one, bigger than both 1 and 3. Now we can check our statistical evidence using the Tukey's HSD test. But at least in the box plot, this is what I'm expecting to find. Now looking down here, comparing 1 and 3, it looks like 1 might be a little higher than 3, but I'm not sure if that's just because of random variation or if that's because 1 genuinely is higher than 3, if design 1 genuinely is better. So that's something my statistical test can provide more information on. And again, even if it turns out that statistically design 1 is higher than design 3, we'd want to think practically, is design 1 going to be meaningfully higher than design 3? That is when I go back to my boss and say, hey, design 1 is 10 higher than design 3. Do they care, even if that's statistically significant? So real quick, let's go on and follow up with Tukey's HSD. So remember, in Tukey's HSD, we can give it this model, number of responses. By design, data equals dat. Oh, I guess we can't. Tukey HSD. Thought we could, but it yelled at me. Oh, I'm sorry. It wants us to give it the AOV. So not give it a new formula. We have to give it the AOV. So instead of giving it the model, let's give it the AOV. Let's give it the mod. That's it. So in this case, we can see that it breaks down by our 2 different factors. Now we're going to ignore this region because, again, we're not studying the region. What we're looking at is the difference in the different designs. So comparing design 2 and design 1, it looks like there is a statistically significant difference between 2 and 1. It looks like design 2 is 175 higher than design 1, and the reasonable range for that difference is between 110 and 240. So if I were presenting this to my boss, I would say it looks like that there's definitely evidence that 2 and 1 are different. So that's the statistical piece. Now, how different, that's kind of the practical interpretation piece. And what we want to go into depth on is this difference meaningful in context? So I don't know what these numbers of 110 and 240 mean, but I'd go to my boss and say, hey, it seems reasonable that the difference could be anywhere between 110 and 240. Does that matter? For the lower end, is 110 big enough to be important? At the top end, is 240, is that just blowing everything out of the water? Is that hyper crazy? Is that pretty much the same as 110? It's definitely a little better, but it doesn't really change what's going to happen, etc. So when talking through a confidence limit with my boss, that might be how I go about it. Is say if I had to put my money on a single number, I'd guess 175, but anywhere between 110 and 240 is a reasonable guess. That's a reasonable amount of difference between Group 2 and Group 1. All right, so Group 3 and Group 1, that was our big question. Looks like there's not evidence that this difference is different than 0. Now note that I start with my p-value and then I move to the interpretation of p-value significant. Because my p-value is not significant, I'm not going to try to interpret this or talk about this with my boss. What I'm just going to say is there's not evidence that 3 and 1 are different. I don't have enough evidence to determine that they're underlying different. Yes, in the sample, they were 17 different. But in the underlying population, I really don't know if they're different or not. So if we did this again, I don't know if 3 and 1 would be different. I don't know, maybe next time 1 would be bigger than 3 instead of being less than 3. And we just don't have enough evidence to determine that if we did it again, 1 is going to be better than 3. So now comparing 3 and 2, it looks like 3 is 192 less than 2, which makes sense. Again, we expect 2, and in our graphic we saw that 2 was the bigger number. The reasonable range for this seems to be between 257 and 127, and again, this is kind of phrased in the opposite direction than we would look because 2 is higher than 3. So the distance 2 is higher than 3 is between 127 and 257. I don't know if that's good or bad. I would go to my boss about that. This p-value is significant, so that means we can have that conversation. We're pretty sure that this is different than 0. And we can have the conversation about the lower and upper confidence limits. Note that as we're talking about the confidence limits, by default, the Tukey procedure provides a 95% confidence limit. You can change that in the options. In fact, I have the options pulled up from when I messed up using Tukey's HSD earlier. But in these options, the confidence level is where we can switch this 95% to be something a little bit different if you wanted to. So if you wanted a 99% confidence interval or a 90% confidence interval to more inform that conversation, that would be the way in which you could have it. So this has been how do we analyze the randomized complete block design data using R. In the next section, again, we're going to be going into Latin squares and then talking about how do we analyze Latin squares data. That is, how do we analyze data that involves 2 blocking factors instead of just 1.